All right, so we just have a couple more examples to look at here before we can wrap up this section. First one is actually kind of a repeat of something we've already done. It's just finding a unit vector in the direction of a given vector. But the reason I'm doing this type of example again is because I wanted to do an example where we have the standard basis vectors being used in our representation. So here I'm saying a equals 3i minus 5k. The fact that there's a k there means that this vector must be in 3 space, because k is not a standard basis vector in 2 space. We only have I and j there. However, one of the standard basis vectors in 3 space is j, and that appears to be missing. That's not a problem, because technically what this is 3i plus 0j minus 5k. And that tells me that the vector a in component form could also be written as 3, 0, negative 5. Okay? Now, how do we find the magnitude of this? Because we need the magnitude in the process of finding the unit vector. Well, the magnitude of a, again, is the square root of the sum of the squares of the components. Okay? That's 9 plus 25, which would be 34. We get root 34 out of this. Okay? Now, we saw previously that finding a unit vector in the direction of a is the same thing as multiplying each of its components by 1 over its magnitude. Or you can think of that as dividing each component by this magnitude here. However, I do want to be careful, because the original vector was given to me in terms of the standard basis vectors. And so for the sake of consistency, I should probably keep my answer in that form. So I'm going to be dividing these coefficients by that magnitude. A over the magnitude of a is 3 over root 34 I minus 5 over root 34 k. So that's the same thing as if I had put it in component form. We're talking about the same vector. Okay. Last example I want to do is an application problem. Now, a lot of the times when I'm doing examples in class, I don't like to pull examples straight out of the text, because usually you can just go and read that. But I really like this example, and I wanted to go through this one with you. This is one that a type of problem that you'll encounter if you take a physics course. It's just like one of the first applications of vectors that you really work with. So what are we looking at here? We have a 100-pound weight, and it's suspended from the ceiling by 2 wires, which we see here and here. The goal is to find the tensions in those wires, which we label T1 and T2. Now, excuse me, taking a look at these arrows here, and understanding what tension is. I understand this is not a physics course, so a tension is a type of force. And if you remember, we said that vectors are commonly used to represent forces. Well, one thing that's been really helpful is looking at the component form of these vectors. So let's think about this for a moment. If I were to put a couple more vectors in here that are going to give me the components, let's say like this. There, and there, like that. Okay? Notice they create these little right triangles. And if you know your geometry, you'll notice that this line that I've created with these 2 vectors down at the bottom and this line right here form parallel lines. The wires form transversals, and we remember from geometry that alternate interior angles are congruent. So that would be a 32-degree angle there. This would be a 50-degree angle right there. Okay? Why does that matter? Well, what I want to do here is determine the magnitudes of these vectors right here. Okay? So let's start with this vector right here. What is the magnitude of this vector right here? Well, I know that the magnitude, if I think of this as a right triangle, in fact, let me kind of blow this up a little bit. we're going to focus on just this guy right here with the 32-degree angle. The tension in that wire corresponds to the length of that vector, or the magnitude of that vector. So what that means is that if the tension if this tension vector is being called T2, then its magnitude or length is the magnitude of T2. That's what I would call that. Okay. Now, from trigonometry, we can use this angle and the fact that this forms a right triangle to find the magnitudes of each one of these vectors using sines and cosines. So for example, it's fairly easy to show that this right here is T2 times cosine of 32 degrees, whereas this is the magnitude of T2 times sine of 32 degrees. And I'm really hoping that you are comfortable enough with your trigonometry to know how I would have shown this. Okay? Now, these are just magnitudes, right? These would be real numbers or scalars. These values are not vectors in their own right. But the point of finding those magnitudes is to see if I can figure out a way to represent T2 in component form, or in terms of what we're actually going to do in terms of standard basis vectors. So here's how we go about that. This vector right here is pointing in the same direction as the two-dimensional vector I, which means this vector is a scalar multiple of I. And because I is a unit vector, multiplying it by this exact scalar that we found right here would give us this vector exactly. Similarly, this vector is pointing in the same direction as our standard basis vector j, and multiplying j by this scalar would give me this vector. And so that tells me that T2 is equal to magnitude of T2 times cosine of 32 degrees I, plus magnitude of T2 times sine of 32 degrees j. All right? That is in terms of standard basis vectors, that's what T2 can be represented as. Now notice that doesn't seem to help us too much because we don't know what these magnitudes are quite yet, but we'll get to that point, okay? T1, let's look at T1. See the right triangle that we have here? T1 is going to have a similar derivation, but there's only one thing that we need to be careful about. You see, in this right triangle, this vector was pointing in the direction of I, whereas this vector is pointing in the opposite direction of the scalar of the standard basis vector I. I points towards the right. This is pointing toward the left. So all that means is that if I figure out the magnitude of this vector, I need to make it negative so that it reverses the direction of that I vector before I multiply it to I. I'll end up with this, negative Ti cosine of 50 degrees I, plus this one doesn't need to be made negative because this vector is pointing up. So that's T1 sine of 32 degrees times j. Okay? And again, like I said before, we don't have what's the word I'm looking for? We don't have information on these magnitudes yet. So there has to be more to the problem to make sense of this. Now, we haven't used the 100-pound weight in any way yet. So this is the point where we want to make use of that. The 100-pound weight, if you think about the force exerted by that weight, that force is acting downward, right? So off to the side, there's an arrow that I could draw here, but I'd be drawing it over my work. I'm going to think of W as the force acting on that weight, okay? Now, the force is acting purely downward. So I'll draw it right here. If that's our 100-pound weight, gravity is pulling it straight down. And the vector that points down is opposite the direction of the j vector. So that means I could get my force W by multiplying a negative scalar times j. Negative because we're pointing down instead of up. What should the scalar be? Well, the scalar should represent the magnitude of the force, which we know is 100 pounds. And pounds, weight, is a force. So negative 100j gives me that. Okay? Now, we're going to use a simple principle from physics to kind of connect some things here. The idea is that these wires are holding this weight in place. And in a certain sense, they counterbalance each other. Your book uses that term. So what that means is that the downward force being exerted by this weight combined with the combined forces of these two tensions should cancel each other out. Or in other words, if I were to add these two vectors, getting the resultant, remember that represents like the net force on these wires being exerted on this weight, T1 plus T2, I should be using these arrows also because I can't do bold, huh? So let me write all those in. There's a lot of them. Little arrows everywhere, okay? That should equal the opposite of my vector W. The resultant of these two vectors, when added together, should give me the opposite of this, so that those two forces cancel each other out. The opposite of W is positive 100J. Okay? All right. Now, I have T1 plus T2 right here, but T1 and T2 I've given in terms of standard basis vectors here and here. So if I actually wanted to add these things together, I technically could. Adding the T1 to T2 and combining the like terms. So I'm thinking of like terms as like the I terms and the J terms. This equation can be written this way. Magnitude of T, that's the one that's negative, so I'll make sure and keep that negative. Magnitude of T1 times cosine of 50 degrees plus magnitude of T2 cosine of 32 degrees. That becomes my I component plus, so that's all of T1, right? Sorry, that's T1 plus T2 with just their I components. Plus the J components, that would give me magnitude of T1 sine of 32 degrees plus magnitude of T2 sine of, you know what, I have a mistake in here. This should be 50 degrees. I didn't catch that before. 50 degrees. Yep. Sine of, so that, yeah, this is the one that should be 50. Oops. Sine of 32 degrees. That's my J component. This is T1. This whole thing is T1 plus T2 once I've combined like terms, and that should be equal to 100J. Now, if you have two vectors that are equal to each other in this form, so in terms of standard basis vectors, we can equate I components and J components. The I component of this vector is 0, so that allows me to set this equal to 0. Negative magnitude of T1 cosine of 50 degrees plus magnitude of T2 cosine of 32 degrees equals 0. And then these I can set equal to 100. So magnitude of T1, sine of 50 degrees plus magnitude of T2 sine of 32 degrees is equal to 100. Okay? What we have here is a system of two equations in two unknowns, where the unknowns are the magnitudes of these vectors. Now, this is a long example, and like I said, this one is in the book. solving for the magnitude of T1 and solving for the magnitude of T2 is simply a matter of solving a system of linear equations. I'm going to jump ahead to the answer. It's a good algebraic exercise to see if you can solve for these. And if you get stuck, look into the example 7 in the book for section 12.2. You'll see the work. But I want to go straight to the answer here. So T1 is going to have a magnitude, once you've computed this and plugged it into a calculator, of approximately 85.64 pounds. Okay? And T2 will have a magnitude of approximately 64.91 pounds. Remember, these magnitudes represent forces, and this force so far has been measured in pounds, so we need to make sure we're using pounds as our unit of measure here. Now, I was asked to find the tensions T1 and T2, not just their magnitudes. The tensions themselves are vectors, not just real numbers. And we have expressions for those vectors here and here. So what I could do is take the two magnitudes that I just found down here, 85.864, 64.91, plug them in to these two representations of T1 and T2, and then simplify and get the vectors representing these tensions. And here's what we end up with if we do that. There's going to be some rounding here, but it's going to come out to about negative 55 I just lost it. I had it pulled up there for a second. Where'd you go? Come back. I had it pulled up here. There we go. Negative 55.05 I plus 65.6 J. T2 is approximately 55.05 I and 34 or plus 34.4 J. Okay? There's a lot to that problem, right? But if you've had a physics class and you've looked at force diagrams and that kind of a thing, this is not unfamiliar territory for you. This is just to illustrate what vectors can be used for, and we're going to look at other applications over the course of this class. But that's going to wrap up 12.2 for us.